Hey everyone, welcome back to my series on low frequency RFID for the Flipper Zero. In this video, we'll learn how the Flipper Zero decodes and emulates 125 kHz RFID signals. We'll also look at how it writes those credentials to a T5577 tag. The next few videos will build on this information, allowing you to extend your Flipper Zero to recognize and emulate currently unsupported protocols. Let's get started. It's been a while since our last RFID video, but I'm excited to jump back into it. In that third video, we created a custom T5577 tag, but that option is no longer in any of the firmwares. At the end of this video, we'll write code for programming a T5577 tag with the custom data from that video. I've cloned official firmware, but you should clone whatever firmware you're running on your Flipper Zero. If you haven't already set up your development environment, I'll add a link to my video and wiki for setup. And if you have any questions, feel free to reach out on my Discord server. All of the low frequency RFID protocols are stored under lib, LFRFID, protocols. For each protocol, you create a .c and a .h file. For example, I created protocol_demo.c and protocol_demo.h. In LFRFID_protocols.h, you'll find an enum with all of the protocols. I added LFRFID protocol demo 1. If you add an entry, make sure that LFRFID protocol max is still the last entry in the list. In LFRFID_protocols.c, add a #include to your .h file, and then add an entry in the protocols array for your protocol. The first value is that enum value you defined, and the second value will be defined in your protocols.h header file. In your protocols.h file, you can see we do a pragma once, so our header's only included one time, and then a #include of the protocol.h so that our code knows about ProtocolBase, and then we do an extern const ProtocolBase and the variable name. The extern means that we'll define this in our protocol's C file. And that variable name was the name we just used over in our registration. At the bottom of our protocols.c file, we define that protocol_demo1 variable. Name is the key type, which is in the RFID file. Manufacturer shows when it's displaying the information. You should generally keep the combination of manufacturer and name fairly small so it doesn't wrap when it's displaying. Data size is the number of bytes in the data field on the RFID file. And features is either ASK if you're using amplitude shift keying or PSK if you're using phase shift keying signals. Validate count is the number of times the same signal had to be received before it's considered valid. If it receives a different signal in between, it resets that counter. So a larger number reduces the chance of error, but it also may take more time to receive the valid signal if there's interference. Most encoders tend to use a value between 3 and 6. The rest of these properties are callbacks in this file, and we'll look at those next. At the top of our file, we have our #include statements, and then we have a #define tag, which is used for logging. We have a protocol demo 1 structure, and this structure holds all of the information for encoding and decoding a signal. Our data array holds the data that's stored on our card, and feed counter is just keeping track of how many times our feed method gets called. Protocol demo 1 alloc is our first callback. It allocates memory for that protocol demo 1 structure, and it returns this pointer. All the other methods that take a protocol parameter will get past this object. Protocol demo 1 free is the next callback, and it gets called to release the memory that was allocated. Protocol demo 1 get data returns a pointer to our card's data. This information is used for rendering the information on the screen. It's also when a file is loaded, this data gets populated, and when a file gets saved, this data gets persisted. Protocol demo 1 decoder start gets invoked at the beginning of a decoding session. Typically, you would clear out any encoded data and reset any kind of state of your state machines. In our case, we're setting a counter back to 0. Next, we have protocol demo1 decoder feed. This is the main function that's used to decode signals. It gets past a level, which is true false, and a duration, which is in microseconds. What you normally would do is see if those durations make sense for the protocol that you're decoding. And if they don't make sense, you would just return false. If they do make sense, you would change your state machine to handle that next bit of data. In our case, we're just looking if the data on the card started with 42, then any signal we get at all, we're going to just increment our counter saying that we're seeing some kind of signal. And then once our signal count gets to 100, we're going to say we have successfully decoded that signal. So this can just pick up static, any kind of static. As soon as it hits 100 signals, we're like, yep, this is the code we want. This happens anytime that the card that was saved is starting with 42. Again, in future videos, we'll look at how to do decoder start and decoder feed for different protocols and actually decode that data. But for now, we're just going to count how much noise we hear. And when we hear 100 signals of noise, we'll call it good. Next, we have protocol demo1 encoder start. And this gets called whenever we're emulating a tag or writing a tag. This would typically reset that encoder state and it would decode the data that's on our card. Next, we have protocol demo1 encoder yield. And when we're emulating a tag, this will get called to ask us that next level and the duration of the level. The duration is measured in ticks, and each tick is 8 microseconds. Unlike when we're doing a decoder and the duration is measured in microseconds. Again, in future videos, we'll look at how to do that decoding and encoding. For now, we're just going to return a level of true and a duration of 1 tick. Next, we have protocol demo1 render data. And this typically renders the information on the card. Let's go ahead and render that as well. So we'll go ahead and add %02x, %02x, data 0, data 1. And then we have render brief data. And this is the same thing. It just should take up less space on the screen. %02x, %02x. And the last callback is protocol demo1 write data. And this is what is used to write back to a T5577 tag. That second parameter, void star data, is actually the T5577 write request that we're going to populate with the data to write. So typically in this method, you're going to call your encoder start, and that's going to take the data that's in your protocol data, and it's going to convert it into what would be sent out. And it's going to use that sent out information to figure out how to program the T5577 block. In our case, we're hard coding blocks 1 through 3 with data from our previous video. You can see from the video, we had FSK2A, a bit rate of RF_50, and we had 3 data blocks. You can also see those 3 data blocks are in block 1 through 3. And then our blocks to write is 4, since we have to also write the configuration block. So now we're ready to try things out. Go to Terminal, Run Task, and then choose Flash USB with Resources. These lib files are part of your firmware, so it's not an application. You're actually flashing new firmware onto your Flipper Zero. Make sure QFlipper is not running, and make sure that you're not running any apps on your Flipper. When our data is not 42, our feed counter does not get incremented, and so it's still 0. And so we need to check 0 mod 100 equals 99 instead of 0 mod 100 equals 0. Once you make that change, do Tools, Options, Flash USB with Resources again. Our firmware was updated successfully. So we'll click OK, go to 125 kilohertz RFID, click on Read, and now put our T5577 tag. And we're reading what the current tag has. And you can see the hex is AA2233. We'll go ahead and back out of that and we'll go to add manually. And now this time we'll find our encoder that we added, the demo one, and we'll start our data with 42. And the last two digits don't really matter. I'll just type in 13 and hit save. And we'll go ahead and just use the default name. Then we'll load the file and write it to our tag. It says success, but really what success means was that we got 99 feed calls. So now we'll go ahead and do a read. So it looks like our protocol data was still loaded and we had 99 samples. So I'll go ahead and reboot the flipper. And then we'll click OK, go to 125 kilohertz RFID, go to read. And this time we see our tag got read properly. So it's no longer AA2233. We now have the facility code of 101 and the card number of 29649 from the previous video. Thanks for watching this video on low frequency RFID protocols. Now you know all the properties to set for your ProtocolBase object. And for writing T5577 tags, if you go to the end of modulation and press Control Space, you'll get a drop-down with the different supported modulations. And in RF50, if you put your cursor right before 50 and do Control Space, you'll get a drop-down of the bit rates that are supported. So if you're using one of the previous videos and you have block 0 configuration data, that's the recommended way to set those values. You can also just type in the hex value here if you prefer. Please like and subscribe. And if you have any comments, please leave them below or on my Discord server.